I'm Grant Hocking with GeoSierra.
In this brief video, we will describe GeoSierra's electric resistive heating for enhanced oil recovery of heavy oil and bitumen. GeoSierra has pioneered the stimulation of ductile formations and is especially known for its design build of permeable reactive barriers filled with iron proppant for groundwater remediation. GeoSierra has shown that it can place these prop planes on azimuth and coalesce to form permeable reactive barriers kilometres in length. In the PRB construction, there is no limit to the height of the vertical propped planes.
The PRB is built from the bottom up with packers placed in the feeder pipe to seal off the injection target area. Here we see a close-up of the packers being inflated. The gel and iron filings are then injected at low pressure, typically 100 to 200 psi, depending on depth, causing the casing to dilate along its entire length, creating a vertical and lateral fracture pathway for the gel and iron filings to follow. The frac wells are injected alternately, with the odd-numbered wells first. This is done in order to harness the power of pore pressure relief, so absolute control of each frac pathway can be assured. The packers from 1 and 3 are then pulled, and the wells are open to the atmosphere, providing the pore pressure relief pathway that ensures a continuous and completely coalesced PRB with no gaps or voids. With the lower section completed, the casings are washed out and the process is repeated to complete the PRB. And again, pore pressure relief assures both vertical and lateral coalescence.
Now, this technology has been modified for oil and gas stimulation and has now been proven down to a depth of 450 meters. The electric resistive heating involves installing vertical prop planes that contain an electrical conductive proppant. In this case, it's a calcined petroleum coke of a medium strength. Electrodes are connected to these planes, and electric current is passed through the plane, and the plane heats up by resistive heating, or sometimes known as joule heating. Those planes can raise to a temperature of 250 degrees C, and by conduction, and in some cases by forced convection, can raise the temperature of the heavy oil and bitumen so its viscosity reduces and it flows to the planes and the wells for recovery. Now, this technology is an alternative for surface mining with only wellheads on the surface and limited infrastructure. Obviously, no tailings, no water usage, reduced carbon footprint, and an enormous reduction in environmental impact. The Subsurface ERG system of electric resistive heating is a very viable alternative to surface mining. And also SAGD. It could be too deep for surface mining, and it could be too shallow for SAGD, or it may have no cap rock, so it has no containment of the steam. So electric resistive heating has a lot of advantages, especially with reduced capex, no water usage, no cap rock required, and it can be applied at both shallow and considerable depth. The calcined petroleum coke proppant has been developed with Ashby carbons and comes in 3 sizes: -8 plus 20, -20 plus 40, and a -40 mesh. It is compatible with GeoSierra's gels for stimulating these ductile formations and will not have any residual and will be placed in vertical planes. GeoSierra's electric resistive heating technology can be constructed from either vertical or horizontal wells. In the case of vertical wells, GeoSierra's dilating cased hole stimulation procedure is followed, while in horizontal wells, an open hole stimulation tool is used. It is interesting to compare performance of the resistive heating say compared with SAG-D in a thick McMurray formation with Athabasca bitumen, say 35 meters thick. Provided the planes are installed through the full pay thickness, the simulations show that the analysis is fairly independent of the McMurray vertical permeability. So we can have some reasonable confidence in the simulations. So let's look at an analysis. In the abscisca, on the bottom is time. The left ordinate is oil production, and that's in green. On the right ordinate is cumulative oil production in yellow. And the far right ordinate is the cumulative electricity-oil ratio, and that's in red. As you can see, we reach a peak, and it slowly drops off, and we get approximately 50% recovery after about 1,500 days. And then we turn the power off, and you can see the oil production as it's decaying quite rapidly in that last few days. Now let's compare it with SAG-D, and we've used the SAG-D, the best SAG-D at Pad C at Mackay River, which is now part of Suncor, that was Petro-Canada. And let's compare the two. And we've plotted the cumulative electricity-oil ratio as an equivalent steam-oil ratio, basically based on the cost of the energy. And you overlay the two, and as you can see there, the electric resistive heating, and this is purely for conduction. There's no forced convection in this analysis. And it's a lot quicker. It's almost produces 50% recovery twice as fast. So even with just conduction, it is a very favorable process, fast, and obviously got big benefits when it comes to less capex and environmentally friendly and small carbon footprint and no water usage. Now the choice between using either vertical or horizontal wells. Let's look at the two. The vertical wells use simple electrodes. It's just basically dumb electrodes, and those electrodes are controlled from the surface for temperature and amount of energy going to each electrode. Vertical wells are also easy to force convect. And that has two benefits. One, it smears out the thermal loading, so all the electrodes will be at a similar temperature and the planes will be as well. And it reduces by a significant amount, the time to recover. And finally, because the time is shorter, it also cuts down your cumulative electricity-oil ratio. There's some benefits for vertical wells. Obviously, if you're deep and it's thin, horizontal wells are required because the capex is much lower. However, the horizontal wells require smart electrodes. There's a number of electrodes along each well, and so the electrodes have to be smart. They have to have a temperature switch and a Coulomb switch. And also, it's difficult to force convect. It's very difficult to arrange. You've got forced convection. So it's a trade-off. If it's thick pay and shallow, vertical wells are the way to go because they also are more robust and can overcome heterogeneities like IHS. If you're deeper and thinner pay, horizontal wells are the best way to go. And there was an in-between ground. They both have very similar recovery rates. The vertical well is possibly a little bit quicker in thick pay because of their full height of the pay and the ability to use forced convection. But very similar when it comes to cost per barrel for operating. CapEx, there's not much in it if it's shallow, but if it's deeper, the horizontal wells win. So it's basically a cost and also risk-reward ratio. The vertical wells, and it's a thick, shallow pay, has a lot more benefits than horizontal.